Welcome to the videos on data converters. So in this sixth part, we'll be discussing successive approximation log to digital converter. Successive approximation converters, so which are popularly known as SCA converters. The fastest code search strategy uses a binary search technique to complete an n-bit conversion in just n clock periods. So now you can see analog to digital conversion is nothing but you are searching for an equivalent digital code for an given analog input voltage. In the previous ADC based DAC based ADC, we have seen that if the input voltage is almost equal to full scale range voltage, it was taking 2 power n minus 1 clock pulses, and which was resulting in a huge conversion time. Here, in case of successive approximation ADCs, there is a fastest code search strategy used so that we can complete the n-bit conversion in just only n clock periods, regardless of the value of Vi. So whether the Vi is very small voltage or whether it is very large voltage, so we're going to end up with converting that analog to digital form with only n clock pulses, irrespective of the amplitude of the signal. I can see this is also a DAC based ADC, but only major difference is, so we have this a different type of register. It is no more a counter now. This is a SAR, which stands for successive approximation register. So we have a SCA register or SAR, which is successive approximation register, which is replacing the counter of a ordinary DAC based ADC. This is also a DAC based ADC, but the major difference is that this register is no more a counter, it is a successive approximation register. We have this DAC as usual, and we have a comparator which compares the output of a DAC with the input voltage. So this is also coming under the category of DAC based ADC. The major difference from the previous discussion and this is the register is not a counter, it is a successive approximation register. So as we saw in the earlier ADCs, we have a start pin which is input, and there is a clock required for this register, and we have a EOC stating the conversion is completed, and we need a reference voltage for this DAC, and the output voltage compared with the input voltage in a comparator. Let us see the working of this successive approximation ADC in the coming slides. Now let us see, of course, this is what we are looking at, a successive approximation ADC. This technique uses a register as a successive approximation register to find, of course, here, okay, how does this will work is, so we will going to find each bit by trial and error. So what we'll do is, we're going to find the output voltage by a trial and error. We're going to find out what is, how do we get the digital equivalent of the analog signal. Now, how does this SCR works is, starting from MSB, you can see now initially MSB of this register is made 1. Starting from the MSB, SCR inserts a trial of 1. So here you can see, if this is MSB, only this MSB is made 1 and all other bits are made 0. So this is going to give, okay, upon getting that start signal, the SCR register makes the MSB 1. It gives a trial to this DAC. The DAC input is now actually MSB is 1 and all other bits are 0. We are going to get a corresponding output voltage to that input digital value from the SCR register with only MSB as 1. That will be compared with the input voltage. I can see inserts a trial 1 and then interrogates the comparator to find whether this value, whatever that is, V0 you are getting because of this 1000, is to rise above Vi. Now you can see, now we have this dotted line as the input voltage that is applied, and we are getting this black a dark line which is the V naught corresponding to this 1000. So corresponding to the only MSB1, we are having a output voltage of DAC over here, whereas the actual input voltage is dotted line. So since the actual input voltage is more than this, or the V naught is still less than the input voltage, okay, now we can see this causes V naught to rise above Vi. Now you can see this is over here. Now if this voltage is above this Vi, then it makes it 0. If this V naught is below Vi, then that 1 is retained. Now we have actually started this as 1 for a given trial. We have made this as 1 and then made all of the bits as 0, and we are trying to see whether that 1 can be retained or should it be made 0. So when do we retain that MSB as 1? MSB will be retained as 1 if that V naught of the DAC is less than Vin. So you can see this causes V naught to rise above Vi. If it is so, then if it does, then trial bit is changed back to 0. Otherwise, it is left at 1. Now, in this particular example, since input is here, the V naught of since the V naught is less than Vin, so we are retaining the bit as 1 here, so it is left at 1. Now the procedure is then repeated for all subsequent bits, 1 bit by 1 bit. Now you can see, so we know how it happens in chemist balance. Suppose you have a weight on one side, you have the material to be weighed on the other side. So you put with some trial that okay, you are going to weigh that for half kgs. When you actually put it, if it is less than half kg, you're going to pour something more. If it is still less, you're going to still pour something more, some more material. Suppose if it exceeds, you try to take out. So when you're taking out, if the taken value is very less, then you have to take it more. This way you'll be keep on different iterations unless that the chemical balance exactly matches with the whatever weight that you put on the other side. Now this will continue for n clock pulses. So that's how the SAR will going to give a corresponding output voltage whenever an input is given. So first it is MSB made 1, then it is compared with the actual input. If the output is less than the actual input, then that bit 1 is retained and you are making the next MSB bit also 1. So when you add that, when you make the two MSB bits 1, that is the most significant, and just one bit lesser significant, you are making that also 1. Then you try to compare that with now this is for 1, this is for 1 1. Now 1 and all of the bits are 0. Now here first two bits are made 1 1 and all of the bits are 0. Now you can see, since it is made, since two MSPs are made 1 1, so it has gone above that, so it has gone above the previous value. Now in such case it will come down. Once it comes down, it makes the other bit as the third bit as 1. So likewise it is keep continuing. This will continue for the last bit. I can see this is how it happens. Following the arrival of the start command, the SAR bit B1 is made 1 with all remaining bits as 0, so that trial code is 100. So we have a trial code of, you can see here, the trial code is 100. This causes DAC to give an output voltage. So we know that with 100 as the DAC input voltage, so DAC will going to give 7.5, but actually the applied voltage is close to 10.5. Now you can see at the end of this clock period T1. So at the end of this clock period T1, so V naught is compared against Vi. So this is the black one is, the bold one is V naught, the dotted one is Vi. Now it is compared. Since 7.5 is less than 10.8, so B1 is left at 1. So this is still retained as 1. And then after the beginning, okay, at the beginning of T2, so this is the T2, at the beginning of T2, B2 is set to 1. So I can see first earlier B1 was set to 1, then you are making B2 also 1. You can see now it is 1 1. So now you have the digital input as 1 1 0 0. So when at the starting of T2 you are making both B1 and B2 1 1. So we have a corresponding output voltage of the DAC which is 11.5. Since 11.5 is greater than 10.8, B2 is changed back to 0 at the end of T2. So this will not be retained at 1 because 1100 is actually giving a output voltage which is more than the desired input voltage of 10.8. So let us see what happens next. So at the end of T2, the B1 is made again. B2 is made 0. So B1 is still 1. Now at the beginning of T3, B3 bit is set to 1. I can see initially we have made B1 1. Since the output voltage of the DAC was lesser than the input voltage, it was retained as 1. Then the next most significant, that is B3 is made 1. When B3 was made 1, so it was going above the 10.8. Now in the before the next clock pulse comes, so at T2 end, what we are doing, we are making B2 0 and we are making B3 1. So B3 is set to 1. Now the actual trial code is 1010. So this is actually B1, B2, B3, B4. So B1 is 1, B2 is made 0, B3 is now made 1. So for this voltage we are getting it as 9.5. So this is 9.5. So since it is less than 10.8, the B2 is left at 1. So now B2 is left at 1. So let us see what happens. So since B2 is left at 1, you make next bit at the beginning of T4, you are making bit 4 is set to 1. So when bit 4 is set to 1, we have 1011 and the corresponding output voltage is 10.5. Now since it is less than 10.5, of course 10.5 is less than 10.8, B4 is left at 1. So as long as the output voltage of the DAC is less than the input voltage, in order to get that we had actually given some input voltage, so that input conditions or input bit positions will be retained as it is and we'll go for next one. So in this particular case, since there are only 4 bits, by the end of the 4th clock pulse we are getting almost an equivalent the digital output with some error of less than half LSB. I can see the actual input voltage is 10.8, so we could able to generate 10.5 with the input with the digital combination as 1011. Note that any voltage in the range of 10.5 to 11.5 would be led to the same code, because we have that error of minus half LSB to plus half LSB. If the input voltage is anything between 10.5 to 11.5, because now the LSB value is 1 volt, because we have taken VFSR as 16 volts. So 16 divided by 16 happens to be 1 volt. Any variation from 10.5 to 11.5 will be represented as 1011. So this way we can see the working of successive approximation ADC. Here the concept is, first you start with MSB bit as 1, that is fed to the D2A converter. D2A converter gives output voltage. That output voltage is compared with the input. If the input voltage is more than the output of the DAC, then you retain that MSB bit as 1. You increment the next MSB bit, so that is made 1. So upon making that 1, we're going to again get some output voltage from the DAC. That DAC output is again compared with the input. If it is more, you bring back that previously made high to 0, then you update the next one. So likewise this continues. You can see even though this is 4-bit DAC, we can able to complete the conversion within 4 clock cycles. So this can be extended for any number of bits. So it will always take those many number of suppose if it is 16-bit ADC, it will take only 16 clock pulses to evaluate the digital